Okay, welcome everybody to this week's HoloTube talk. It's a pleasure to also welcome Benjamin Wisses from University of Southampton. And so he will talk in this week about does the hydrodynamic series converge? So we are really looking forward to your talk, Ben.
Okay, thank you, Martin. Yeah, pleasure to be here. Thank you for inviting me. I've enjoyed many of these HoloTube talks online and happy to be a part of this series. So as Martin said, the question I'm asking, does the hydrodynamic series converge? And this is based on a slightly older paper I wrote, and also some more recent work with Michal Heller, Alex Cervantes, Michal Spolinsky, and Victor Svensson. One of these papers was out a few months, and the other one hopefully will be out this month. Good. Please do just interrupt me if you have any questions. Just unmute yourself and start talking over me. That's absolutely fine. So why are we interested in hydrodynamics? Well, one reason is that it is ubiquitous. And by that, I mean what you need, what we're really studying are the conserved currents near equilibrium. So here's an example of the stress tensor. We have a conservation equation for the stress energy T mu nu. And we would like to, in addition to this conservation equation, we have a set of constitutive relations for this current. So for T mu nu, we write it as an ideal piece plus pi mu nu. And the idea is we write down the most general thing we can here, which is consistent with the symmetries that we have in our theory, which might be conformal symmetries, for example. And we would like to write this constitutive relation in terms of the hydrodynamic variables. In the conformal case, that would be the temperature and the velocity. And you write down every tensor structure that you can think of that is permissible by the symmetries into this object here. And there are then infinitely many such terms you can write down. And so the way you organize those is to count the number of derivatives, where the ideal piece has no derivatives in it, and the pi mu nu encodes things with one derivative and higher. So we can split pi mu nu into a sum over n from n equals 1 to infinity, where n labels the number of derivatives in each term. And if you want, you can introduce the formal parameter lambda raised to the power n, and if you count the numbers of powers of lambda, that tells you how many derivatives there are. So this is a convenient organization in the sense that it measures deviations away from equilibrium. As you approach equilibrium, the more and more derivatives you have, the idea is that those become less and less relevant as you approach equilibrium. Of course, to each tensor structure, if you just use symmetries to constrain the tensor structures, you have undetermined coefficients in general. And these you would label as transport coefficients after you've fixed some ambiguities. And these transport coefficients are where the information about the microscopic theory come in. So far we just used conserved currents and symmetries. And then if you were to give me a microscopic theory, like n equals 4 superyoung mils, you could then compute the individual coefficients that appear. So it's these coefficients that encode the microscopic data. So this procedure, this hydrodynamic procedure, is ubiquitous. It describes many of the things we observe around us in everyday life, but also it describes these more exotic things like quantum field theories or strongly interacting quantum field theories, the horizons of black holes, and so forth. So because of this ubiquity, it is interesting to ask some formal questions about this. And as my title indicates, the first question I would like to ask is, does this sum here over the number of derivatives, is this convergent or not? So it's a very formal question, but this is the first question we would like to ask. And as a second question I would like to ask along the way is, can you recover information about the microscopic theory by performing a resummation of these terms? So what I mean by that is, if you start with a microscopic theory and you construct these constitutive relations, computing these transport coefficients, can you undo that process? Can you say, I'm going to perform a suitable organization of these terms and resummation of these terms so that I learn what the original microscopic theory was? Is this step invertible or not? So that's the second question. Okay. So if you've not noticed, the organizers of HoloTube appear to put a picture alongside everyone's talk on the website. I don't know who is responsible for this, but this is the picture associated to mine. It took me a little while to figure it out. But I think what they're saying is, the question is to converge or not to converge. That is the question. So this is, I attribute this to the HoloTube organizers. Is that your work, Martin, or is that someone else? No. So this is very, very clever. Thank you. I enjoyed this. So that's the question we're asking. So let's make this a little bit more specific. Let's look at conformal hydrodynamics. So this specifies what symmetries we have in the problem. So this covers a wide variety of microscopic theories with all having the same group of symmetries. And in this case, as I mentioned, you have a velocity field, hydrodynamic variable, which appears here, these u mu's, and you have a temperature. And this appears implicitly in these other functions. So here's the energy density, the pressure. The pressure is really an equation of state, so it's a function of the temperature. Here the metric, which I'm just going to keep flat for this talk. And then at the derivative orders, we begin with one derivative term, and the only term you can write down in the conformal theory is the shear tensor. So this is just one derivative of the velocity field appropriately symmetrized, and the coefficient, the transport coefficient associated to it, is the shear viscosity. And as you go to higher orders in gradients, there are more and more terms you can write down. I've presented only a few of them here. So this is second order, third order, and so on. All I've done here is to show the first few that appear after you linearize. So there are more terms that you should write down: second order, third order, fourth order. But these will vanish in the linearized limit. This is just for clarity of presentation. But you get the idea that you can write down these terms and you give them each a transport coefficient after you fix the redundancies. And as I mentioned before, these transport coefficients are fixed by microscopic details. So if you have any quantum field theory with an Einstein dual, it is known that this is given by eta is 1 over 4 pi s for the shear viscosity. So this is the first few orders. And in general, it's hard work. If you want to go to third order, for example, you can work, do a lot of work to compute all the different tensor structures that can appear. But this can't be the route that we want to take, because we want to compute the radius of convergence of this series. So we need to compute basically a very large number of these terms. So we'll fix our attention on a specific observable in which we can compute many orders in the gradient expansion. And to do that, we also need to know the microscopic theory, since each of these transport coefficients will be fixed by some microscopic theory. So this turns out to be particularly straightforward if you pick holographic theories with Einstein duals. So then what we're really talking about are the properties of black holes. And in this context, it is relatively easy to compute for specific quantities a very large number of orders in this series. So holography to the rescue. All right, so that leads me to the plan of the talk. We'll begin by talking about the Bjorken flow, which I'll say happened around 2013 in this holographic context. Then dispersion relations around 2018, and recently these results about real space results, which I'll come to at the end, which was from this year. And as a spoiler to the answer to the question in the title, does it converge? Well, the answer is there's no intrinsic microscopic answer. So if you give me a theory, I cannot tell you whether the hydrodynamic expansion converges or not. Instead, what I can give you is a condition. So the expansion is conditional on the momentum space support of any given solution. So if you give me a microscopic theory and a solution, then you can get the answer. And if you give me just the microscopic theory, I can just tell you the condition. So the condition itself is intrinsic to the microscopic theory. So hopefully that made sense.
Sorry. Can I ask, do you choose any particular frame when you write this expansion?
We work in Landau frame, but because we're never truncating in our approach. Well, it depends which section we're talking about, I guess. So for this last section, I guess you're asking about this last section.
Yes, precisely.
We work in Landau, but we never truncate the series. So I don't think this will affect anything. It's just if you keep if you keep formally the sum from 1 to infinity, then the frame transformations are just redundancies. So I don't think that will affect any of the results.
Okay.
But maybe we'll get to this section, and then you can ask me again if you're not happy.
Hi Ben.
Hi.
Sorry.
Hi.
Since you've been interrupted, can I interrupt you a bit further?
Yes.
So when you proceed, it's important to distinguish linearized hydrodynamics versus nonlinear.
Yes.
And so when I want you to actually make this very explicit where that assumption is made, because
okay.
As you well know, two derivatives can be basically a second gradient of the velocity or the first gradient of the velocity squared.
Yes. I will be very.
So I would say that I'm not sure how robust it is if we look at the sort of the conclusions depending whether it's just linearized hydrodynamic or it's fully nonlinear hydrodynamic.
Yes, I completely agree. I completely agree. I'll be very clear about when it's linearized and when it's not, and we'll return to this interesting question in the discussion at the end.
Awesome.
Yeah, thank you. That's definitely, that's an important thing to mention. Thanks. Yeah, so this is basically the message. This message here, okay, I'll be explicit here. This message I'm presenting is the linearized message, this conditional message. Good. The other annoying thing that I will apologize for now is I will use both the letter Q and K for spatial momentum. So in this section 2, I'll use Q, and in this section 3, I'll use K. So sorry about that. But there we go. So I'll just review briefly this work that was done by Michal and collaborators in 2013. And of course, there's been a lot of interest in this topic, and I'm afraid I haven't given you credit, everyone else, but sorry about that. I'll just discuss this paper. So the idea is we're in this topic, they were interested in boost invariant flow. So boost invariant flow is interesting for people who work on heavy ion collisions, for example. And the setup is roughly what's depicted in this diagram. You have one space direction, time direction, and then many transverse directions. And the idea is you have this beam, X is basically the beam axis for colliding two ions together, and depicted by these red arrows moving at relativistic speeds. And of course, these objects are supposed to be pancaked by the relativistic effects. And so when they collide, you're basically looking at two colliding pancakes. And so one approximation you can make is to ignore the dynamics in the transverse directions. So you restricted non-trivial dynamics in this plane, this TX plane. And then the products of this collision will be present in the forward light cone. And the assumption you make is that it depends only on the proper time tau. So the proper time tau is on the slice given by this hyperboloid t squared minus x squared. So then you're solving on these constant tau slices. And the observation that was made is that this large tau expansion is basically the same thing as the hydrodynamic gradient expansion. So if you expand, for example, the energy density, so this is a component of the stress tensor, in a large tau expansion, so a late time expansion, it's perturbative in 1 over tau to the 2/3. And this perturbative expansion is in correspondence with the hydrodynamic gradient expansion. So they computed this expansion to order 240, these epsilons to order 240. And what they found was that this series is a divergent series. So in particular, these coefficients En grow factorially with n, which indicates to you that it's divergent, has a zero radius of convergence. So when you're faced with a series which has a factorial growth, the standard toolkit that you can employ is this Borel transformation. And the Borel transformation basically removes this n factorial and gives you something that you can attempt to resum. And the way you do that is with a Pade approximant. And by doing this technique, you can find basically branch cuts in the Borel plane, which correspond to new contributions when you invert the Borel transformation. And so one of the contributions that they found was that the a correction to the energy density is something that goes like e to the minus tau to the 2/3. Now this was a perturbative series in 1 over tau to the 2/3. So e to the tau to the 2/3 is actually a non-perturbative contribution, which explains why you would not see it by doing a perturbative expansion here. And this you can sort of expect because, after all, if you look at black holes, we know that there are higher quasi-normal modes, and quasi-normal modes have frequencies which go like the temperature times time, and the temperature in this case for the background Bjorken flow is diluting over time. It's an expanding plasma, and it dilutes like tau to the minus 1/3. So when you put these two things together, you get e to the tau to the 2/3. So this is the expected behavior of a transient on top of this Bjorken flow due to non-hydrodynamic quasi-normal modes, which are non-perturbative in this hydrodynamic expansion. Okay, so that was just a lightning summary of this work. I'm sure many of you are familiar with it.
Ben?
Please, hi.
Hey, sorry, just this is me being probably a bit stupid, but can you explain the tau to the 4/3? Because epsilon should have dimension 4 and doesn't tau have dimension 1 minus 1?
There's probably an energy scale, so epsilon 2.
This is a conformal theory, right?
It's conformal theory.
There's an overall scale, Heidlef, that enters, and it's defined by epsilon 2, and it propagates to epsilon 3, epsilon 4, etc.
Okay.
So sorry, Ben. So in this particular computation, this computation is done in fully nonlinear.
That's right. Yeah.
So are you aware where this has been repeated? Linearizing, does it even make sense to ask about linearized Bjorken flow on top of equilibrium?
No, I don't think so.
That's what I thought. So it's
right.
just yeah.
Yeah, that's right. So indeed, the connection between this and real space results for linearized hydrodynamics is lacking. We would like to make a better connection, and indeed to do that we would need to take into account nonlinearities.
But we know, okay.
However,
we know nonlinearities will make it divergent, and linear will make it convergent, as you explained.
Well, maybe we'll see. Yes. So the point of I guess part 3 of this talk will be to elucidate the connection between the momentum space dispersion relations and the real space linearized hydro, and this is one step towards connecting these two areas. But yes, not yet the full picture.
Sorry to come back to my question. So actually, the night scaling works in terms of temperature, I guess. Is T of tau, should I think of it as some kind of time-dependent temperature?
T to the 1 over 4. Oh, T to the 4.
Yeah. So then that works. And then this additional energy scale, it comes in when you want to resolve the time dependence of this temperature scale.
Yeah. Yeah. Okay, thanks. Okay, so yeah, good. This is just a quick summary. And the reason I mention it, of course, is that this was for a long time the only work that had been, that at least I was aware of, looking at the large order behavior of hydrodynamics, at least in holography, and the answer was a divergent result. And so for a long time, it was said that this expansion was divergent. Okay, so now let's turn to dispersion relations. So this is based on a paper I wrote in 2018. So for dispersion relations, what do we mean exactly? Well, we just take those equations of motion we wrote down earlier, and we look for linearized solutions around equilibrium. So we'll look for, and because we're working on Minkowski space, let's just look at plane waves. So there's some momentum q and some frequency omega. Of course, when you plug this into the equations of motion, it tells you the relationship between omega and q. And as a series in spatial momentum, the omega leads with a diffusion. For the shear channel, it leads with some diffusive behavior. And then there's a series in q squared. So we can write down this hydrodynamic series. Omega is sum over powers of q squared with coefficients omega n. So this is the quantity. So in the last part, we were interested in the energy density at late times. Now we're interested in the frequency as the series in spatial momentum. It's a different observable. So in the case of a black hole, this is obviously one of the long-lived quasi-normal modes of the black hole. So yeah, let's ask about this series. And so for this paper, what I focused on were quasi-normal modes of ADS4, Rise, and Nordstrom. And the reason for doing this was I remember this paper by Danny in the chat now, and Simon Gentle, where they had these amazing movies of these sort of intricate trajectories of poles dancing around each other in clover leaf shapes and all sorts of stuff. So this was a very interesting and intricate system at finite density. And so this is why I focused on this, because I knew something interesting at least would happen. And so here's what the spectrum of this theory looks like at some value of the charge density for the quasi-normal mode spectrum. So for quasi-normal modes, what you're interested in is basically the frequency, real and imaginary parts as a function of real momentum. So this is what it looks like. And you can see that there's lots of stuff happening. The first thing to note is that this piece here is the hydrodynamic piece. This is all shear channel. So this is the expansion I was talking about before. If you're able to construct this function as a series in Q around this point, you get the hydrodynamic expansion that I mentioned earlier. But then, of course, you have all of this other stuff going on. You have all of these other transient modes, these non-hydrodynamic quasi-normal modes, which appear with imaginary parts for their frequencies as Q goes to 0. So what distinguishes these from this is that as Q goes to 0, these have a non-zero value, and this goes to 0, Q goes to 0. And so then, obviously, lots of interesting things happen. So there's this classic sort of mode collision happening here. As you increase the real part of Q, they collide with each other. So I just wanted to ask, well, what is the radius of convergence of this series? So I just computed these omega n's to order 80 and look at the ratio test. So we divide subsequent terms in this series, omega n divided by omega n minus 1, the previous term, and I weighted it by some scale Q star. Q star is energy density plus pressure divided by the chemical potential and the square root of the shear viscosity. When you construct this quantity, you see it converges to -1. So this plot is 1 plus this quantity as a function of n, and it approaches this limit at a rate of 1/n. So in other words, the radius of convergence of this series is finite, and it's set by Q star. So this Q star is the radius of convergence of this shear mode dispersion relation. The origin of this radius of convergence is a singularity that appears not at Q star, but at plus minus I Q star. And one way you can see that is by doing a Pade approximant of this series data. So the part A is you take this series omega n is a series in q squared, and you instead write it as a ratio of polynomials such that when you expand this ratio for small q, you recover this series. So it's a way of reorganizing this expansion. And when you do this and plot the poles and zeros of this function in the complex q plane, what you'll find is this following picture. There's a 0 at the origin because that's the hydrodynamic definition. Omega goes to 0 as q goes to 0. But then you see there's accumulation of poles and zeros starting at q star, I q star, so along the imaginary q axis. So this alternating condensation of poles and zeros emanating in an array that comes from the origin is the clear indication that this is a branch cut, and this point here is a branch point singularity. So what you learn, therefore, is that this series, the radius of convergence of this series, is set by this branch point singularity in the complex q plane. In other words, there's a square root here. You should view this whole thing as one sheet, and then it becomes connected to other sheets along this branch cut, and the point where it degenerates is the branch point singularity. So we should now think about this omega of q as really being this multi-sheeted Riemann surface in the complex momentum plane. So you can do that, and let's just plot, for example, the imaginary part of the frequency as a function of momentum. In the previous diagram, we just saw the top sheet, but now we're showing more than one sheet. So this point here is where we started. This is the hydrodynamic series. So as q, this is the origin in the complex momentum plane. And you can do a Taylor expansion around this point, this hydrodynamic series, and that describes this first sheet up to this point here. This point here is that square root branch point, this singularity. So this radius of convergence is set by the closest singularity. So you're looking for the closest singularity to the origin on the hydrodynamic sheet. There can be other singularities. There's one here, but it's not, and it's closer to the origin, but it isn't on the hydrodynamic sheet, so it does not set the radius. This, of course, is the transient, the non-hydrodynamic quasi-normal mode, and as I mentioned, this is another branch point. So this is just the first couple of sheets, and if you were so inclined, you could plot many of them because it's easy to construct the dispersion relations for black holes. You can just do that without doing the hydrodynamic expansion. You can just solve the equations of motion, and you find that there are essentially infinitely many sheets, and they all seem to be connected to each other. So if you go through this branch cut, you enter another sheet, and it's really a labyrinth. And it looks like you can get from here all the way down as many sheets as you want in a continuous fashion. So let's take a different viewpoint. Let me go back. Let's now cut this. Let's draw this as a function of. Yes, hi, please.
Just to make sure, I think I understand what's going on in this plot, but just to make sure that you call transient non-hydro QNM. The blue guy. This is the purely imaginary mode that was.
No, this is a pair. This is a pair of complex. This is purely imaginary.
Plot on your previous plot, the 2D plot, the one that where you were referring to Danny and Simon.
Oh, right, but this is real Q.
Yeah.
I'm going in the other direction. So we're going into imaginary Q. So that would be in this direction over here.
Yes.
So if I were to go along this surface out of the plot, carry on, you would see another branch point here along the real Q axis.
Right.
Okay, so this branch point occurs on the imaginary Q axis. You see, so if I slice this at imaginary Q equals to 0, I get the Danny and Danny Bertin and Simon Gentle plot.
Yes.
Right, but that does not include this singularity. So there'll be plenty more branch points, and they're all over the place. It's just really messy.
But I thought that in this plot, what I was really supposed to understand is that then your hydro mode collides as a function of purely imaginary Q.
Yes.
With the blue guy, the first blue guy from Danny and Simon's plot.
Yes, that's right. Yeah.
That's right. Okay, good.
Yeah. Sorry. Yeah, exactly. So this if you go in complex Q, this guy collides with this one.
Good. Okay. Good.
Yeah. Thanks. So indeed. So let's draw that exactly that slice. Let's take real Q equals to 0, and we get to here. Okay.
Yes. Good.
Thanks. Okay. Thanks, Blaise. So we have hydrodynamics, which is the Taylor expansion around this point on the hydrodynamic sheet. We have this branch point singularity at imaginary Q. We have the non-hydrodynamic mode, which is in general a pair of complex modes. And then we have this additional thing which kind of comes into the mix. If you were to look at the hydrodynamic expansion, so if you just took this naive sum of terms, summing Q squared to the n, and you did a partial sum, so if you took the first 80 terms and you just added them together, literally, and you plotted that, then this will give you the green line. So clearly, this is the point at which it diverges, as you'd expect. So of course, from this picture, you recognize this phenomenon as this branch point singularity is really a mode collision. So of course, we've known about mode collisions for quasi-normal modes for a long time. But here you see it's occurring, as Blaise was asking, at imaginary Q. So it's a non-real value of Q. So you would not necessarily see these if you were looking at quasi-normal modes, but here they are. So these set the radius of convergence, and I don't think it was appreciated before that these collisions set the radius of convergence. Okay. So let me make a cautionary remark. So you may wonder why Q star was determined analytically, and the reason is because it appears actually in the equation of motion. So if you look at the equation of motion, there's a square root containing Q and this quantity. So you can already figure out that this has to be one of the singularities of the dispersion relation. And so for some reason, you know now that how this is set analytically. And from this, you can conclude that, well, as you take the chemical potential to 0, so as you approach the neutral limit, this branch point location goes to infinity, because it goes like 1 over mu. However, this does not imply that the radius goes to infinity. As I mentioned, what you have to do is look in the complex Q plane and look for the closest singularity to the origin. As you send mu to 0, this will no longer be the closest singularity to the origin. So it does not follow that the radius goes to infinity. And as we have seen, there are many other branch points. So we've seen at least 3 or 4 other branch points in this talk. And so one has to track all of them and look as a function of the chemical potential, which ones are setting the obstruction to convergence. I mention this as a note of caution because there have been several papers which incorrectly concluded that because Q star goes to infinity as mu goes to 0, that the radius goes to infinity. But this is not true. So I'm putting this as a note of caution. So the statement is that the value of Q that I've been plotting, this branch point Q star, does set the radius of convergence. So the question is, what is the full picture as you start varying Q? So this was answered in a very nice paper by Aaron Janssen and Christiana Pantelidou. So they extended basically this analysis of radius for Reis-Nordström to all values of the charge. So the example I've been presenting sits around here in the middle, I think, on this blue curve. So this blue curve is the analytically known branch point sitting at plus minus I Q star. So that's this one. And as you can see, as Q goes to 0, the charge goes to 0, the chemical potential goes to 0, and this goes off to infinity. But before you get there, there's another branch point that comes in, this red one, and this takes over as the dominant one. So this is the closest singularity to the origin on the hydrodynamic sheet for values of Q less than 0.23. And then similarly at large Q, so as you approach the extremal limit, another branch point takes over, this green one, And interestingly, as you maybe might anticipate, as t goes to 0, this branch point moves towards the origin, suggesting that the radius goes to 0. So this is all a plot from their paper, and I encourage you to read it. What's curious, I find, is that you can determine the blue curve analytically, but you can only determine this interval numerically. So it's curious that you have an analytic expression for the radius of convergence within some interval of charge, but you don't know what that interval is analytically. So that's kind of curious. Okay, so let's try and summarize, please.
So Ben, then the other lines, they're just guide to the eye. So maybe.
So what they did several things in this paper. The circles are the perturbative expansions computed, and then they do the ratio test, I believe. Right, so this is really computing the series data. And the lines, this blue line is this analytic known result. And this red line, I think, is if you compute the singularity location exactly using numerics.
You mean tracking the collisions?
Yes.
Okay.
So the solid lines are tracking collisions in the exact answer. When by exact, I mean perturbatively exact. Not using perturbation theory, but using numerics. And the circles are doing perturbation theory and checking the radius by looking at the ratios, I think. So they find good agreement, of course. Okay.
Yeah.
Thanks. So let's try and summarize the answer to question 1 in this case. What time is it? Okay, let's try and summarize the answer to question 1. What I'm advocating is that we treat the omega of Q, a complex Q, as some Riemann surface, and the radius of convergence of the hydrodynamic series is then given by the closest singularity to the origin on the hydrodynamic sheet, of course. What we saw was that this singularity was a branch point type, in other words, a square root, which we normally refer to as being a mode collision in holography. And this was for radius rides Nordstrom at some fixed value of the charge. And there have been several other examples. The cleanest one you can do is probably this Muller-Israel-Stewart or BR-SSS constructions, which are sort of toy microscopic models, which include a hydrodynamic sector as well as a transient non-hydrodynamic quasi-normal mode. And if you, of course, those dispersion relations are already known and they have a square root in them. So this is kind of obvious now that you look at it. It's a square root singularity and has a finite radius of convergence. In this case, I think the singularity is on the real Q axis. And then there was 2 papers by these authors, Grozdanov, Kopton, Staronets, and Tadic, where they looked at ADS5 in the neutral case, so Schwarzschild. And then, as I mentioned, there's this paper by Aaron Janssen and Christiana Pantalidou, where, as we've seen, the results already for ADS4 rise and Nordstrom for all charge, but they also did, I think, ADS5 rise and Nordstrom for all charge. So it seems reasonable on the back of this sort of evidence to propose that these the radius is set by these branch points, these square roots, these mode collisions. But I wouldn't say that there was a proof yet. I mean, this statement, the most generic statement, is talking about singularities. So you would have to exclude other types of singularities. But it seems reasonable, again, on the back of this evidence, to propose that there are always going to be mode collisions. I don't know of any counterexamples. I should highlight also something that was put forward in these papers, which I would say is mathematically distinct. They put forward the proposal that the radius is set by a critical point of a spectral curve. So I'll just mention that here, and if you want to find out more, well, you can read their papers, or Andre gave a talk on this holotube series several weeks ago, which I can recommend. All right, now let's turn to the second question. Can we recover any of the microscopic information by resummation? So recall this picture for the multiple sheets of the dispersion relation. What you can do is you start on this first sheet with the Taylor series, the hydrodynamic data, and you can attempt to analytically continue it through the cut. So you go from this sheet onto the second sheet. And one way you can do that is you use, instead of the variable q, excuse me, you use another variable, let's say z, complex variable z, which is related to q in a quadratic fashion, in such a way that in the variable z, there is no branch point. So you can sort of unwrap this square root and go from 2 sheets into 1. And after you've done that trick, this series will converge all the way from the origin to the origin on the second sheet. It's a little bit more complicated because of the second singularity, but that's the basic idea. And it works, which I found very surprising. So here's the result of that procedure as a function of hydrodynamic order. So I take, for example, this series to hydrodynamic order 9 and do this analytic continuation and read off the value at the origin on the second sheet here. And then I increase the order to 11, 13, and so on, up to the max order, which I have, which is 79. And the order 79, you can see as a function of doing this, it converges to a value. And at order 79, there are 4 significant digits of agreement between this analytically continued result and the exact answer, which you can just compute by computing this first quasi-normal mode of the black hole. So it's a pair, a complex pair of modes. So this procedure, this analytic continuation procedure, goes from hydrodynamic data to microscopic data. So I would like very much to see a sort of more systematic way of doing this, but I'm unaware of one that works. Okay, so that concludes the discussion of dispersion relations. So if anyone has any questions about dispersion relations, that would be a good time. Otherwise, I'll move on to the real space results, the more recent results.
Sorry, can you say again how precisely you do this analytic continuation? How precisely you do this?
How do I? Yeah. So of course the details are in the paper, but in this paper. But the idea is we know that q minus I q star. There's a square root of if you have a square root of q minus I q star basically in the formula. So what you want to do is replace q minus IQ star by z squared. That's the data. That's the variable replacement that I do. So when you take the part A summation of this series and you replace q by z squared in that way, and then you compute the result. When you undo that variable transformation, you go back from z to q, you have 2 sheets to choose from. You have the plus and minus roots for z. One of those roots will give you this, and the other root will give you this. So it's basically unwrapping this square root into a single sheet. You do the part A to sum on that sheet, and at the end, you go back to the original 2 sheets, and in that process, you have to pick which sheet you want. And so there are 2 results.
Okay, thank you.
Yeah, so the details are here in this paper. Thanks. Any more questions about dispersion relations?
Yes, I would like to ask a question as well.
Yeah.
So you said that there are 2 sheets. So one is the hydro sheet and the other one is the microscopic sheet.
Mm-hmm.
I guess I have missed the relation. Why one is the microscopic sheet? Could you comment on that once more?
Why is one microscopic and one not?
Yes.
Well, just because I mean that this one has a 0 at the origin.
Okay.
So when q goes to 0, omega is 0 here, which I'm taking as a definition of the hydrodynamic sheet.
Okay.
Yeah.
Thank you.
Of course, in this case, there are infinitely many sheets. And here's another cut. This blue line is another cut. And
Okay.
it's a real mess for this black hole case. Okay, so this is more recent. Place.
The way of saying that this one is microscopic in some sense is that these complex poles at zero wave vector, they don't come from the IR retarded Green's function.
Okay, but if you were to but doesn't the IR retarded Green's function contain all the transport coefficients?
So, but by that I mean the retarded Green's function you would compute in the infrared geometry, the ADS 2 plus R2.
Okay, but does that only include a subset of these?
It only includes the
Q squared
imaginary guys, the black lines on Simon's and Danny's plots.
Okay,
but not these complex guys, which you get from appropriately matching to the UV. So in that sense, they're more microscopic than other non-hydrodynamic poles.
you're saying that they're not intrinsically near horizon.
That's right.
Yeah. Okay. Yeah, that's interesting. Okay. Thanks. Okay, so this was work with Michal Heller, Alex Cervantes, Michal Spolinsky, and Victor Svensson. And of course, in many talks, you see pictures of collaborators put up, and this, 2020 has been a real disaster. And of course, everyone has been working from home and remotely via Zoom. So I just thought I'd show you a group photo of us in our natural habitat. So here's Michal, here's me, Alex, Victor, and Michal. So the basic question is, what does the real space divergence that you might see in Bjorken flow have to do with these properties of dispersion relations that I've been discussing? And has been preemptively pointed out by Alex. What we're going to do is consider linearized hydrodynamics, and of course, in doing so, Bjorken flows are strictly excluded. But nevertheless, I think there's an important connection to be made by considering real space linearized. So let me just discuss that, and then we can come back to Bjorken flow at the end and decide whether it is of any relevance. The key step, I would say, in this analysis is a reorganization of time in U. So traditionally, you would pick a frame, and you also have a redundancy associated to equations of motion. And the choice there seems to be arbitrary, but one choice you can make is to replace any time derivatives that you see by spatial derivatives, or series and spatial derivatives. And you can do that because the leading order hydrodynamic equations are just the time derivative of the hydrodynamic variable equals something. So you can, every time you see a time derivative, you can replace it by its equation of motion and a series in spatial derivatives. So this is a redundancy of the description, and we can do that without loss of generality. And we do that in Landau frame, as I mentioned. So once you've done that, it's relatively easy to enumerate all possible tensor structures that can appear in the linearized theory. So the first one is, of course, very familiar. It's like the spatial shear tensor. So it's spatial derivatives of U in this way. The second one is two derivatives acting on the energy density. And the third one is two derivatives acting on the divergence of the velocity. So here, velocity is really the spatial part. Because again, we're linearizing around equilibrium. So this is a two derivative object, this is a two derivative object, sorry, this is a one derivative object, this is a two derivative object, and this is a three derivative object. And these are the only tensor structures you can write down, plus spatial Laplacians acting on them. So the most general constitutive relation is the following. Pi j L is a general function of Laplacians, spatial Laplacians, acting on the shear tensor, a general function of spatial Laplacians acting on this 3-derivative object, and a general function of spatial Laplacians acting on this 2-derivative object. And each of these functions, we can encode them as a series in spatial Laplacians. So for example, A, we write as a sum over del squared n with coefficient an. And we can do similarly for B and C. So all of the transport coefficients of this theory are now captured by an, bn, and cn. And this is completely general. So now we can do a little bit of counting. Well, we know that this has 1 derivative, so this contributes to odd orders. This has 3 derivatives, so this contributes to odd orders. And this has 2 derivatives, and this contributes to even orders. And so at first order, you find there's only 1 transport coefficient, which is A0. At each subsequent odd order, you find there are 2, because there's A3, and then, or A1, and then a contribution from B. And then at each even order, you have 1, which are the C's. And if you think about it, these countings of 1 to 1 matches precisely the number of coefficients you expect to find in the shear and sound dispersion relations expanded order by order in K. And this is not a coincidence. You can actually map 1 to 1 these ANs with the coefficients that appear in the expansion of the dispersion relations. So here's an example for the AN sector. You only need the shear mode dispersion relation. And basically AN is the 2n plus 2th component in the series expansion in K, with similar results for B and C. So you can think of this as a kind of matching calculation. If you give me a microscopic theory with a specific shear and sound dispersion relation, you can series expand it, read off these ANs, and that tells you the hydrodynamic constitutive relation to arbitrary order. So that's the first step. Now what we want to do is consider, for example, a shear mode. So we're going to perturb around equilibrium with a delta U. This is a fluctuation of the velocity. And it's shearing because, well, we've got the fluctuation in the first slot and the dependence is in the last slot. So this is X. So when you evaluate the contributions to the pi mu nu, this is the only contribution. It's a sum over ANs with 2n derivatives plus 1 acting on this solution U1. So this is now the constitutive relation evaluated on this shear mode. We would like to ask, well, does this sum converge or not? So let's look at the root test. So we're going to compute this quantity C, which is the limit superior as n goes to infinity of this quantity, an derivatives of un. So an derivatives of u raised to the power 1 over n, and then you take n to infinity. So this is evaluating whether this stress tensor is convergent or not, much like you would do in the Bjorken flow when you ask whether the energy density is convergent or not. That was an example of a question for currents. So we're asking a question about currents in the linearized theory. If C is less than 1, then it converges. If C is greater than 1, it diverges. So we can actually evaluate this knowing what we know about the coefficients. So since these ANs, let's take this first piece, since these ANs are given by the shear dispersion relation, and we already argued that we generically expect that these dispersion relations have a branch point at some k star. From this, you can conclude that an grows geometrically, and in particular, this limit of n goes to infinity of an to the 1 over n goes like 1 over k star squared. So a consequence of these branch points at k star, it tells you about this large order behavior of these an coefficients. So this is one piece of this convergence test. The second piece is this purely spatial derivatives of U. So here, for this, we invoke this Paley-Vena theorem, and we say that if U is compactly supported in momentum space up to some maximum momentum, K max, then by this theorem, in position space, it's an entire function of exponential type K max, which means this limit superior of these derivatives to the power of 1 over n is actually K max squared. So these are the two key results, and then we put them together, and of course you get K max squared over K star squared as the answer for C. And so if the limit of support in momentum space is lower than the branch point location, is smaller than that, then this current converges. And if it's greater than that, this current does not converge. So one point to make is that this the statement about support in momentum space, it just pertains to this solution. So if you give me a solution, you have to ask, you can look at its Fourier transform and ask if it's compactly supported or not. But because it's linear, you can ask that question at any moment in time. The support in momentum space will not change as a function of time because there are no nonlinearities. So in particular, if you want, you can evaluate this condition already on the initial data surface. So you can evaluate this condition C just on initial data if you want. So let's take a look at that in practice. So the simplest model to work with is Muller-Israel-Stewart theory, of course, or BRSSS. As I mentioned, it's a toy microscopic model, second order, so it has two modes. It has a hydrodynamic piece and a non-hydrodynamic piece. And these ANs that I mentioned, these pieces that appear in the constitutive relation, they're given by some diffusion constant. They're given by a relaxation time associated to the transient mode. And these coefficients are the Catalan numbers. And when you insert this and you pick some initial data, so here we pick this sort of Gaussian with a cutoff. So it's like a bandwidth limited Gaussian. So above K max, this is 0. Then you find precisely the results that I outlined earlier. So if you look at the ratio test as a function of the number of terms that you keep, if you pick this K max to be less than K star, it converges. So the ratio test approaches something that's less than 1. If you pick K max to be greater than K star, it diverges, but it does so geometrically. And if you pick K max to infinity, so that it's not compactly supported anymore, then you find factorial growth. So naively, this is, from a naive point of view, this is consistent with Bjorken flow in the sense that Bjorken flow, if you cut it open on initial data surface, or you pick some time slice, it will not be compactly supported in momentum space. But of course, there are caveats to that, as we have already discussed. Yeah, so any questions about this part of the talk?
Ben, this is something I've played with at some point, but I can't remember the answer. I thought that in BRSSS, I can't remember how many Yes there are, sorry. You have to do this trick in order to see this artificial transient mode of rewriting the second order constitutive relation as an extra conservation equation for the dissipative part of the shear tensor.
That's right. So in MAS and BRSSS, you have divergence of T, but you also have an equation that governs time mu.
Right, but if you don't do that,
time mu is independent variable.
If you don't do that, then you don't see this transient mode in the constitutive relation. And then my question is, when you substitute time derivatives with spatial derivatives, as you did a couple slides back, are you still able to keep this transient mode?
No. So I think once you get rid of the time derivatives, you only have, if you were to truncate, so if you do this rearrangement where you replace time derivatives by spatial derivatives and then you truncate, you're only ever going to have one omega.
Right.
So it's projecting out the non-hydrodynamic stuff,
Right.
which is exactly what you want to do because it's hydrodynamics.
Yes.
The stuff that you get, if you truncated hydrodynamics with a time derivative in it, the stuff that you get, the extra modes, are not physical. They're a result of the truncation.
Yeah.
So this is what you want to do. You want to get rid of those time derivatives. And then you understand what theory you were describing.
So then I'm confused. How come you can play with this toy microscopic model where you do keep the transient mode? Since
no, I mean this data is the hydrodynamic sector data. So the hydrodynamic piece. So you can do this you can take MIS and you can do the procedure I outlined where you replace time derivatives by spatial derivatives. And then you'll get an infinite series.
Mm-hmm.
And those coefficients ANs are these Catalan numbers. And that has a finite radius of convergence because there's a square root. If you sum these Catalan numbers, you get a square root. So you write AN to the QN and sum it. You'll find the branch point that's there in the microscopic model.
So how come then you did this with MIS and not say n equals 4 superior Mills Schwarzschild radius, right? Just for
this is way easier to do.
Yeah. Okay.
Yeah. Yeah.
Okay.
Yeah. Because we can write down these ANs to all orders like that. That's it.
Mm-hmm.
Which we could not do we'd have to compute those numerically.
Okay.
N equals 4. But yeah, I mean, that would be an equally valid example. I think you would see the same happen. Okay, thanks. Any more questions? Well, maybe I can summarize, and then if there are more questions, we can have them at the end. So I'll summarize the talk. As I was outlining, I think it's useful to view this omega of Q as basically a multi-sheeted Riemann surface where you take Q in the complex plane, and then the radius is the value of Q for which there's a closest singularity to the origin on the hydrodynamic sheet. From all the examples that I've seen, it appears to be set by mode collisions or square roots or what you would call a branch point singularity of the Riemann surface. We then explored the consequences in real space. We looked at linearized hydrodynamics. We proposed this new way of organizing it in purely spatial derivatives. And by doing so, we were able to map these coefficients in the constitutive relation to the dispersion relations of shear and sound. And this gave you a direct connection between real space convergence properties and the location of branch points that appear in omega. So the definitive answer to the main question, at least in linearized hydrodynamics, is that convergence requires that the momentum space support not exceed the location of these branch points. So in the end, I think it's a very neat answer that the condition is intrinsically microscopic because the location of the branch point is intrinsically microscopic. But evaluating the result, you need to know something about the solution, for example, the initial data. Then you can check whether the momentum support does or does not exceed this branch point. A tangentially rated point is I think these two things are often conflated, convergence and applicability. The point I would just like to make is even if this series diverges, you can still look at optimal truncations and it can still be applicable. Of course, question 2 I have not answered in real space about resumming and obtaining microscopic data. And this is something that we're addressing in upcoming work. Essentially, you want to do a Fourier integral, and there are some new non-perturbative complex saddles of this integral. I think it's very interesting, and that will hopefully come out this month. As has been asked, we would like to know about interactions. Does any of this that I've said apply when you add interactions? In particular, one of the things we relied on is, well, one of the things we mentioned is that the compact support is independent of time. So this is no longer true when you add interactions. The support can change over time. And so can there be a mechanism where there is compact support? And so one thing you might ask is, well, maybe in reality, you don't really describe the UV, you put in some cutoff. So lattice is important, or real physical lattices. The other case, which I think is possibly interesting, is turbulence. So we saw in a talk by Christiana a few weeks ago about turbulence, and the region that wasn't really discussed in that talk is this region, the UV. And here in a turbulent flow, the power is directly cascading to the UV where it gets dissipated. So this looks like a natural mechanism for which the power at high K is removed. So the one question is, how does this compare to K star? How does this momentum scale compare to the branch point location in the dispersion relations? All right, so I'll end it there. Thank you very much.
Yeah, thanks for your very nice talk, Ben. So we already had plenty of questions, but of course we can have a few more questions. So
Can I have a comment, please?
okay, please go ahead.
Yeah. So thank you. It was a very nice talk. So I really want to bring this thing because there is a very simple, well, okay, in my view, a fairly simple way to see a difference between linearized and nonlinear hydrodynamics.
Mm-hmm.
So let me see if I can draw something. Okay, good.
Okay.
So
do I need to stop? Oh, you're on my screen. Okay. Yeah.
Yeah. Unless you mind.
No, of course. Go ahead.
Yeah. It's just so. For example, when we talk about say in a linearized hydrodynamics, so I can say there is basically nth derivative of u, right? And so that's the only one that would happen in linearized hydrodynamics. Mm-hmm. Now, if I include nonlinear hydrodynamics, then I can have del n1 u del whatever, and 2u, actually del, basically k terms like that, as long as, the power adds up. And so it's very easy to see.
I can't see anything you're writing, but yes.
Oh. And so, yeah, and so basically what I'm saying is that at the same order in the gradients, mm-hmm. there are factorially more terms in a nonlinear hydrodynamics as it is in linear hydrodynamics.
Yes.
And so that's, for me, that's a very compelling reason why nonlinear is divergent. So I absolutely agree with you that at this stage, we basically have only holography to define a hydrodynamics for us. Yeah. Because in a holography, we can basically compute a stress energy tensor, and then we can reinterpret it any way we want. Mm-hmm. And it's not to say that one is better than the other, it's just that they are very different. So when you do the linearized truncation, it's one thing, and that's not what, for example, the full stress energy tensor from holography will tell you. And I think this is also related when you talk about interactions. That's implicitly, I guess, those are, I can interpret these nonlinear terms, at least to low order, as exactly the interactions you are talking about.
Yes, exactly. Yes.
And so, yeah, and I completely agree with you that that's also related to the question of a compact support. Because, for example, in the presence of nonlinearities I just mentioned, your compact support will not be time invariant. It will be changing precisely because you have interactions. So I think it is a little bit misleading, especially the way how I was initially reading your papers as claims sort of, we have this convergent and we sort of solved the problem. It just basically related to the initial condition. I think it's important to emphasize the restrictions, that mm-hmm. it's under these particular limitations that the conclusions are made.
Yes, of course, I agree. Yeah, I guess we did not make any claim about nonlinear case, first of all. But yeah, I agree with you that nonlinearities are surely going to be important. What did I want to say? Yeah. I mean, yeah. So the way I would present this is to say that one step towards the goal of understanding the nonlinear case is to take the dispersion relation results and relate them to real space linearized. So I think that's the natural first step, which is what we did. And already there, I think you can still ask the question, is it divergent or not? And
but it's
restricting,
it's expected.
One point of view you can make is that restricting to compactly supported initial data is very unnatural and would never happen. In which case the answer would be divergence, even in the linear theory.
Yeah, but again, so if I do holography, I'm just simply getting wrong results if I follow your route. Because, you know, if suppose I wouldn't have, I'm just saying that there is a dramatic difference between a linearized hydrodynamics and a non-linear one. And so if I wouldn't be able to basically I'm saying that if I compute using linearized hydrodynamics, whatever, somehow using some other techniques, right? So a lot of things in holography we can do both ways. For example, sometimes using localization and sometimes using, you know, exact holography, and we get the results. And so I am saying if there would be some other tools, something along the lines that you are trying to develop to basically sum up the linearized hydrodynamics, I will get a wrong result. It will not correspond to holography because holography will be including all these, you know, nonlinear gradient corrections. And I claim that they are dramatic. You get completely different results.
I don't disagree that the nonlinear corrections are important, but we just have not addressed those. That has not been part of this study. It is.
No, yes, I am saying, but you know, it's just the example of the in this unique example where we know what the non-equilibrium physics is, which is holography. And I claim that in that framework, we know that that's not linearized hydrodynamics, end of story. It goes way back to the, you know, if you wish, the, you know, the early paper of Andre and company, where they were saying that, well, there are these, you know, there are nonlinear corrections. I mean, these nonlinear terms. And I'm not even talking about, you know, the long time tails, but that's a different story, even in the large N.
I don't dispute any of this. I'm not denying the existence of nonlinearities. I'm acknowledging it here, and I'm saying this is an important question, but I think it's a next step. And it is not addressed by our paper. I agree. But I also think it's important, and I agree with you entirely that those corrections will be important for deciding convergence or not in outside of a linearized regime. Of course, you can always linearize around equilibrium, even for a black hole.
Yeah, but I'm just saying it's not just convergence. It's just, you know, it has order one effect. That's what I'm saying. The terms, once your higher order terms will become important, I can write you down n factorial more terms, which have the same, you know, which have the same order of importance. We used to think about effective field theory of hydrodynamics. Well, we are thinking about hydrodynamics as an effective field theory. And what I'm saying is that the effective field theory you are constructing by limiting yourself to linearized hydrodynamics is simply inconsistent with, you know, what we know from holography.
It's not inconsistent. You can always linearize holography.
Yeah, you can, but why would you do it? I mean, if you know what's the right thing, what's the right physics, right? I agree, yeah, you can do it, but...
because in the linear case, you can solve and obtain the condition for convergence, which is what we did.
But they are wrong.
In the linear case, that is very difficult to do in the general setting. So the reason that we linearized in this talk, in this paper, was so that we could answer the question in the general real space flows in a linearized setting. If we had not linearized, we could not answer the question. Just because it's very hard. That does not make it inconsistent. It's perfectly consistent. We're just not claiming to say anything about the case where you include interactions.
Okay. Well, I'm going to get other people to talk, but thank you.
Oh, thanks, Alex.
So I see two more raised hands. So first was Peter Tadic. So please go ahead.
That's clapping. That's not raised.
Oh, sorry. Okay, so then next is Michael.
Actually, I was also clapping. But I can just add like one or two sentences to what Alex was bringing up. And I think I think like this work that Ben discussed towards the end of his talk might have something to say for the nonlinear case, because also in the nonlinear case you might introduce lattice, and the lattice is going to regulate for you like you know, how many momenta you have in your system. And I mean, this provides an additional knob that has not really been explored in the study of convergence or divergence of nonlinear hydro. And one can try to utilize this knob to learn something also for the nonlinear hydro. And I guess, I mean, I agree with you that in the nonlinear hydro case, there are many more terms that can appear simply because of nonlinearities. However, what we show in this work that Ben discussed is that well, like these terms are not essential in having a divergent gradient expansion, right? If you have you know, the support of your initial data as all momenta. However, of course, like what you see at the nonlinear level is going to be affected by them.
I absolutely agree with you.
This is how I see it.
It's a very good point that, you know, of course, we know about level crossing from quantum mechanics, and that's basically what is discussed here is, you know, is an analog of a level crossing in quantum mechanics in linearized hydrodynamics. And we know that that's indeed produces, it's also the, you know, the complex analysis, right? The basis of complex analysis. And I agree with you that this hasn't been appreciated, that's a way how you can get divergence as well. It's that I'm pushing a little bit on the other side, the way regarding the broadness of these conclusions. Though I also appreciate that in building up on this work, it's also important because it will help understand to which role the interactions start bringing up the other route of divergence as you established with Romuald years ago, this n factorial growth. And so I think that's I'm not trying in any way to diminish this. So that's an important thing, but it's also important to understand limitations.
Okay, so are there further questions? So this seems to be not the case. Then again, thank you very much for your very nice talk, Ben. And we have next week also another talk. Okay. Thanks.
Great, thank you.
So I